This lecture will cover the RISC-V branch and jump instructions, rounding out the basic instruction set needed for our class CPU. Branch and jump instructions interrupt the execution of consecutively stored instructions. In other words, the program counter normally updates using an offset of 1, in which the value is incremented by 1 every cycle, or every fetch. Branch and jump instructions potentially cause the program counter to change with an offset that is not 1, but is a value that is encoded in the instruction. Branch instructions cause this to happen only if a certain condition is true, while jump instructions do this unconditionally. For Lab 3, we'll ask you to implement 6 branch instructions, specifically BEQ, which is branch if equal, BNE, which is branch if not equal, BGE, which is branch if greater than or equal, BGEU, which is branch if greater than or equal unsigned, BLT, which is branch if less than, and BLTU, which is branch if less than unsigned. Notice that there's a conspicuous lack of the branch if greater than and branch if less than or equal, based on all the different types of comparisons you can do between two numbers. We have no branch if greater than, and we have no branch if less than or equal. Why is that? Well, there's a reason. It's because our ALU only supports the SLT and SLTU comparison operations. And greater than or equal is just the complement of branch on less than. In other words, A less than B, or rather not A less than B, is A greater than or equal to B. RISC-V has 3 different instruction formats that it uses for the branch and jump instructions. Branch instructions use the B format, which includes a 12-bit immediate field that serves as the branch offset, or that holds the branch offset. The offset bits are not encoded in consecutive order, though. They're kind of scattered around the instruction. Also, unlike MIPS, where the branch offset from the instruction is multiplied by 4 before it's used, the offset in RISC-V B-type is multiplied by 2, which is to accommodate the 16-bit version of the RISC-V instruction set. This is the reason why, if you look at the instruction format, the B-type format, IMM sub 0 is not shown in there, in the instruction encoding. In other words, there's a 12-bit immediate in the B-type, but the bits are labeled immediate sub 12 down to immediate sub 1, since bit 0 is implied to be 0, which is caused by the implicit multiplication of the immediate field after it's extracted from the instruction and before it's added to the PC. So here I'm showing 2 tables. The one on the left shows the mapping between the instruction bits and the offset bits, but this is sorted by the instruction bits in reverse order, 31 down to 0. While the table on the right is the same information, but I resorted the rows of the table according to the offset bits from 12 down to 1. Admittedly, I had to create the first table in order to make sense of the instruction encoding, and then to create the second table, which is what I used to construct the system verilog statement, which combinationally sets a signal called branch offset, which is shown here. Notice that I append a 0 to the right side of the branch offset, which effectively shifts it 1 bit to the left and multiplies it by 2. This makes it a byte address offset, and also makes the bit pattern consistent with the numbering used in the instruction format, the B-type instruction format. Now that we have the branch offset, we add it to the PC to get the branch target address. However, which PC do we use? we have a pipeline CPU, so we actually have 3 PCs, technically, which represent the address of each of the 3 instructions that are in flight in the pipeline. Currently, your design probably only has a signal for one of the PCs, and it's called PC_fetch, which is holding the address of the instruction that's currently being fetched in the fetch stage, which would be the address of the instruction that comes after the branch instruction if you have a branch instruction being held in the execute stage or in instruction_EX. You can add a register to the PC fetch to delay it 1 cycle and obtain PC_EX, which would be the address of the instruction that is in the execute stage, which would also be the address of the branch instruction in question, or the branch instruction that you're decoding, the branch instruction that you're examining in the execute stage, and for which you're also calculating the branch target for. So this would give us PC_fetch, which is the address of the instruction being fetched, and PC_EX, which is the address of the instruction being executed. This is an important question because it affects how the branch offset is calculated by the assembler. For example, if the branch offset is 0 and we're adding it to PC fetch, then the target would be the instruction that appears after the branch, which we also refer to as the fall-through instruction. Or it's the instruction that would be executed if the branch is not taken. However, if we add the offset to the PCEX, then the branch target would be the branch instruction itself, meaning that it's branching to itself, which would result in an infinite loop consisting of 1 instruction. The instruction set architecture documentation doesn't really help us here. It's a little vague because it only refers to the PC without defining whether the PC is the address of the branch instruction or the address of the next instruction that appears after the branch in the program, or the fall-through instruction. To figure this out, I wrote a branch instruction in RARS that branches to itself and found out that it set the offset to 0 in the machine instruction, meaning that the offset is being added to PC_EX, which is the branch offset is relative to the branch instruction for which you're calculating it for. Now this might seem obvious, but that is not how MIPS worked. MIPS calculated the branch offsets relative to PC fetch, which is the instruction that appears after the branch. So MIPS was different. As a result, we can use this statement to compute the branch target. Note that despite having appended a 0 to the branch offset, I deleted 2 zeros from the right side of the branch offset when calculating the branch target, since our instruction memory is word address. So in other words, I calculate the branch offset according to the RISC-V spec, but then we customize the branch target for our CPU, which is different than a normal RISC-V processor in the sense that its instruction memory is word address. So the branch offset is the immediate from the instruction multiplied by 2. The branch target is the PC_EX added to the branch offset divided by 4, or shifted to the right by 2. Now in this statement, I'm assuming that your PC is 12 bits, so I sign extended the offset by 1 bit. We have one jump instruction, and it has its own format, the J format, which includes a 20-bit immediate that is also shifted 1 bit to the left to make it a byte offset, much like the branch. So in other words, the J format has a PC offset included within it, but it is a longer offset. It is a 20-bit. It is a 20-bit immediate field. This offset is also like the B type. It's the offset is stored in non-consecutive bits inside the instruction format. So once again, I created some tables to help me out here. These tables and these two system verilog statements hopefully will help you in decoding or extracting the offset and then computing the jump offset and the jump target addresses. The 20-bit or effectively 19-bit word offset. So again, in the J-type, you have essentially effectively a 21-bit byte offset or a 19-bit word offset. But in either case, that is actually larger than our 12-bit program counter. So we don't need to assign extend in this case when adding the offset to the PC_EX. This instruction is unconditional, unlike the branch instructions, but it also writes the current PC value into the RD register for the purpose of saving a return address, which the callee, which is the code you're jumping to, can use to return at some point back to the caller code. But which PC do we write to the register file, PC fetch or PCEX? Well, since the intent of the jump and link is to store the return address, which is the address, or should be, the address of the instruction after the jump and link instruction, then we would want to write PC fetch to the register file. This way, when we return from the callee to the caller, we will return to the instruction that appears immediately after the jump and link instruction. But there's a catch. Because the register, the link register, is written in the write back stage, not in the EX stage, which is the write back, remember, is a cycle after the jump and link is executed. We are going to have to delay the PC fetch one cycle, as we do with REX when writing back an ALU result. But since the PCEX is already the delayed form of PC fetch, we can just simply use PCEX when writing back. We don't have to add any additional delays. This might seem confusing, but when the jump and link writes back, the jump and link instruction is in the write back stage when it's doing that. And at that time, the PCEX is the address of the instruction that is in the execute stage, which is the instruction that occurs in the instruction stream after the jump and link instruction. And that's the correct instruction you want to write back. In other words, you want to write back the address of the instruction after the jump and link, which when the jump and link is in write back, that instruction will be in the execute. So you can connect the PCEX signal directly to the register file mux, which is the one that, if you remember, is controlled by the reg select _ write back signal. Finally, we have the jump and link register instruction, which is an I-type instruction. This instruction uses the unshifted 12-bit immediate field as the offset, but not a PC offset. Instead of adding this offset to the PC, it adds it to the, in your CP, what would be the read data 1 _ EX signal, which is the contents of the RS1 register. Actually, you may have named that signal in the A _ EX signal if you use the same naming convention as the one I used in my Lab 2 tutorial. So again, the instruction, it has a 12-bit immediate, as all I-type instructions do, but that immediate is used to add to the contents of the RS1 register, which is the value that comes out of the read data 1 output on your register file, but may be called A _ EX inside of your CPU module. Like the jump and link instruction, it also writes the current PC, or actually the PC of the instruction that follows the jump and link register instruction, into the RD register. One problem with the branch and the jump instructions is that, scratch that. One problem with the branch and jump instructions is that the target calculation and the branch resolution, which would be the actions of the ALU to determine if the branch is taken or not taken, happen when the instruction is in the execute stage. But by the time this work is complete, the fall-through instruction will have already been fetched. In other words, by the time we realize that we need to branch or jump, it's too late to influence the outcome of the fetch stage because the execute and fetch stage are operating concurrently. For this reason, every taken branch instruction and all the jump instructions must replace the following fetched instruction, the instruction immediately behind it in the pipeline, with a stall or a no operation instruction. The easiest way I've found to do this is for the control unit to output a signal called stall_fetch, which signifies that the instruction that's in the fetch stage should be converted into a stall as it transitions from fetch into the execute stage. This signal is delayed, the stall_fetch signal that is delayed one cycle using a register, and then becomes the stall_ex signal, which is used as an input to the control unit that instructs the control unit not to write any registers or change the PC as a result of the instruction that's being executed. In other words, the stall_ex tells the control unit to treat the current instruction as a stall, even though the instruction itself will still have been written into the instruction EX register. So in other words, the instruction that appears immediately after all your taken branches and all your jumps will still be fetched, and you'll still see it in your pipeline. It will still enter the EX stage, but you'll also see a stall_ex signal that accompanies it, and that will signify that that instruction isn't going to be executed. It's going to be treated as a stall. As is typical with RISC-V, the changes required to implement these instructions into your existing design are minimal. It's pretty neat. I mean, you would think that you have to make a lot of changes, but you don't. You only need to add the branch ADDR-EX, JAL ADDR-EX, and JALR ADDR-EX signals, which I showed you how to compute those earlier. Each one of those signals is the computed target address for the B type, the J type, and the I type branch and jump instructions. And the reason you need 3 is because each of these 3 formats calculate the branch or jump target differently. So we have to calculate all 3 for every instruction. These 3 signals, along with PC+1, which is the normal PC offset when not executing a taken branch or jump, are fed into a mux that will feed the PC fetch register, and that mux will be controlled by a new signal called PC source_ex. So the PC source_ex is the way for your control unit to perform a branch or jump instruction. That along with the stall_ex. So when PC source ex is 0, we'll select PC fetch +1 will be the next value of the PC fetch, and the stall, of course, will be 0. But if the PC source_ex is 1, 2, or 3, which would select one of the 3 targets, then the stall_fetch signal should also be 1. As I mentioned earlier, you will need to add a delay to the PC fetch signal and call it PC_ex. And you will need a new control unit output signal called stall fetch and a new control unit input called stall_ex. Finally, you need to add PC underscore EX as an input to the reg select mux. This allows us the ability to write back the value of PC underscore EX for the write back stage. In the control unit, you'll need to add the ALU output, which is R underscore EX, as an input. So the control unit needs to be able to use the ALU output as an input, since the control unit will determine whether a branch should be taken. So the ALU and the control unit will work together to resolve branches to determine whether a branch will be taken. For the BEQ and BNE instructions, the control unit will instruct the ALU to perform a subtract, which will subtract the contents of the RS1 and RS2 register. And then the control unit will set the PC source EX to 1, selecting the branch target, and stall fetch to 1, only if the output of the ALU is 0, meaning that the two inputs of the ALU are equal. For the branch if not equal instruction, the ALU will still perform a subtract operation, and it will still set the PC source to 1 and stall fetch to 1, but only if the output of the ALU is non-zero. For the BLT and BGE instructions, the control unit will instruct the ALU to perform a set on less than operation, and it will set the PC source EX to 1 and the stall fetch to 1 only if the output of the ALU is 1 for the BLT and 0 for the BGE, because the SLT will only produce a 1 or a 0 output for the ALU. So BLT will branch if the SLT result is 1, BGE will branch if the SLT result is 0. For the BLTU and BGEU instructions, the control unit will instruct the ALU to perform a set on less than unsigned operation and set the PC source to 1 and stall fetch to 1 only if the result from the ALU is 1 and 0 respectively. So the only difference between BLT, BGE, and BLTU, BGEU is whether the ALU is performing an SLT or SLTU operation. Everything else is the same. Now, Lab 3 will require you to add these new branch and jump instructions to your CPU. I wrote a test program for you to use when testing your CPU. The test program will take your CPU through a complex sequence of branch and jump instructions, and it gets kind of confusing, but you can validate your program, or rather you can validate your CPU design executing the program by checking the PC fetch sequence against the one that's shown here and in the slides. I believe this is the correct fetch sequence. So determining whether this program works involves checking your program counter sequence and making sure that it matches this one. We will also ask you to write your own test program, similar to the way we asked you to write a binary to decimal converter for Lab 2. This time, instead of converting the binary input on the switches to decimal and displaying the decimal value to the hex displays, we will ask that you write a program that computes the square root of the value set on the switches and display the result in base 10 on the hex displays using 3 whole digits and 5 fractional digits. So the hex displays will have an implied decimal point after the first 3 digits. So 3 digits, point, 5 digits on the hex displays. The easiest way to do this is to use a binary search algorithm, which works by making a guess at the square root, checks the guess by squaring the guess and comparing the result of that to the input value, and then reduces, or rather decreases or increases, the guess appropriately according to whether it guessed too high or too low. But it also halves the adjustment amount by 1/2 each time. So this allows you, as you go, you make smaller adjustments to converge on the right answer. Your input value, since it comes from 18 switches, will span the range of values from 0 to 2 to the 18th power minus 1, which is 262,143. If you take the square root of both ends of that range, you get a range of square root values, output values, that will range from 0 to 511.99902. Remember that we're displaying 5 fractional digits on the hex display, so we're hoping that if you put all the switches up, the answer will be 511.99902. If we set our initial guess to the halfway point between 0 and 511.99902, which is almost 512, the halfway point there is 256, and our initial adjustment value, which I refer to as the step, can be initially set to half of the initial value, which is 128. So we'll start guessing at 256 and we'll start adjusting at 128. So let's consider what happens when we ask the program to compute a square root of 500. The first guess is 256. When we square that, it's 65,536, which is too big. So we reduce our guess by 128, which gives us 128. 128 squared is 16,384. Too big. Bigger. It's larger. It's greater than 500. So we have to reduce our guess again, but this time by half the step. So we reduce it by 64. So 128 minus 64 is 64. 64 squared is 4096, which is again too large a value, so we decrease our guess by half the step. Brings us down to 32. 32 squared is 1024. Again, too large. We decrease our guess by 16. 16 squared is 256. Okay, now we're too small because 256 is less than 500, so we increase our guess by half the step amount. So we increase from 16, and we increase by 8, so that brings us up to 24. 24 squared is 576, too large, so we decrease our guess by 4, brings us down to 20. 20 squared is 400, too small, we increase our guess by 2, brings us up to 22. 22 squared is 484, too small, we increase our guess by 1 to get 23. 23 squared is 529, which is too large, so we decrease our guess by half the step. Now remember, our prior step was 1, so we are now at a step size of 0.5. So 23 minus 0.5 is 22.5. 22.5 squared is 506.25. Too large, so we decrease our guess by half the step size, which brings us down to 22.25. And we can continue this until the step becomes too small to represent in our data format. In our case, we'll use fixed point as we did in Lab 2. And since our input is coming from 18 switches, which is an integer, we are limited to having at most 32 minus 18, which is 14 fractional bits, which will allow for a minimum step size of 2 raised to the minus 14th power, which is 0.00006. Our initial step is 128, or 2 to the 7th power. So when we add the 14 fractional bits to our step, in other words, shift that step 14 bits to the left in order to add our fractional bits, which will initially be 0. This will turn on bit 7 plus 14, or 21. So when the value of 128 is a value where bit 7 is 1. When we insert the 14 fractional bits, we effectively shift, left by 14 bit positions. So the result of that will be a value of all zeros except for bit 21 being set to 1. And if we shift that step, if we divide the step by 2 each time through the algorithm, shift it, which we'll do by shifting it to the right by 1 bit, that means that after 21 shifts, that bit 21 will have been shifted off, and the step will become 0. So this means that the algorithm will iterate 21 times. We'll shift the step 21 times, at which point the step will become 0, and that's when the algorithm will know to stop. Since we were using 5 fractional base 10 digits when displaying the answer on the virtual DE2-115, we will see on the hex displays a minimum increment, a minimum value of 0.00001, 4 zeros and a 1. So our algorithm may produce an answer that may have an error that is as high as twice the step size, or 0.00012. Now, in the case of 500, when we run through the algorithm, it turns out that the answer that would be displayed would be off, would have an error of 0.00004. For debugging purposes, I wrote an Excel spreadsheet that performs this algorithm for you for an arbitrary input value, which you can download from Moodle. Now, one thing to keep in mind is if your algorithm finds an exact square root value, in other words, if the square of the guess matches the input value exactly, then it needs to bail out. It needs to exit. Otherwise, if it continues, it will end up producing an incorrect answer. To display the result to the hex displays, you need to multiply your final guess value by 10 to the 5th power, or 100,000, and then delete the fractional bits, and then convert the resultant value to decimal using your code from Lab 2. Be aware that all your multiplies will require the full 64-bit product. So use the mul-hu and mul instructions to obtain all 64 bits. So when squaring your guess, you'll be multiplying 2 values having 14 fractional bits. So the product will have 28 fractional bits. That doesn't leave a lot left over for the non-fractional bits. So you'll end up having to shift the product 14 bits to the left to get rid of the extra fractional bits resulting from having squared the value, the guess, in order to compare it with the input value, which we assume will have just 14 fractional bits. So why? Because when you compare two fixed point numbers, you need to make sure that both values being compared have the same number of fractional bits. But when you multiply, you get more fractional bits. So what I'm saying is, after you square the guess, you have to readjust it. You have to shift it to the right and delete the extra 14 fractional bits that you get from having squared the value. For this, you'll need to shift the low part of the product, of the lower 32 bits, right 14 bits, which is pretty clear. But then it's a little more complicated, because then the high value, you're going to have to shift that left 18 bits. And then OR together those two values. This will effectively allow you to shift the bits from the high part down into the low part. So in other words, you're doing, the objective is to shift the high and low values together, concatenated together to the right by 14 bits. That means that part of the high value will make its way into the low value. So in order to do that in your software, you'll take the, basically you want the 14 bits, the low order 14 bits that are in high, you want to shift those up to into the upper 14 bits position, which you can do by left shifting by 18 bits. And then you can recombine the shifted low and the shifted high values together into one value. And you also need to do this when multiplying your final guess value by 100,000. In this case, the reason for this, now 100,000 is an integer that would have 0 fractional bits, so the product of your final guess and the constant of 100,000 will still just have 14 fractional bits, but when you display those two, your hex displays, you don't want to have any fractional bits. So you still have to shift your final guess multiplied by 100,000, you still have to shift that 14 bits to the right, and to do that, you need to perform a shift of the high and low bits of the product together. Now, if you're still a little unsure about this, I have detailed pseudocode for the algorithm, for this algorithm in the lecture slides. So you can translate the pseudocode from the lecture slides into your RISC-V assembly code, and that should be relatively straightforward. And as always, if you have any questions, feel free to contact us on the forums or through direct email. Thank you.